One orange. Oh, green one. And there, orange is ahead. So I was trying to think of a game that everyone has played. And the problem with that sentence is that I use the word everyone. Like all-encompassing. Everyone. And not everybody likes games as much as me. In fact, I'd venture to say that most people don't like games as much as me. So I had to think simple. Even simpler than Camel Up. Which is a great game, but we're looking for something everyone has played. So I thought of a game that I do think everyone has played, and it's called Heads or Tails. Don't think it's a game? Well, think about it. You have two sides to play the game, two teams, and at the end you're going to have one winner and one loser. In fact, I don't think there's even a chance of a tie because I've never seen a coin land on its side, though I hear it's possible. So the question then is, why do I like this game so much? Well, the thing I like about this game are the stakes. That means what people are playing for. I've used a coin, play heads or tails to decide where I'm going for lunch. King's Row, got it. I've even seen people use it to decide bigger things. But then there was that movie, Dark Knight, where the Joker used a coin just like this to decide if people lived or died. Now, that's a little too far, and thank goodness that's a movie. So we're going to take the stakes back a little bit. And let's say, instead of the lives of people, we played for the life of an Oreo. Now, this Oreo, while innocent, isn't going to make it to the end of the video because either heads, it goes on the blue plate, and I get the Oreo, or tails, it goes on the yellow plate, and my kid gets the Oreos for lunch tomorrow. Which kid? I'll flip a coin. Now, let's see what happens. Heads. Looks like I'm eating an Oreo. So, what were the odds of me getting the Oreo? Well, there were only two outcomes, either heads or tails. And were they as equally likely to happen? Well, if I do a fair flip, looks like tails came up this time. So they were likely to happen. There was a just as good of a chance of heads as there was tails. And as long as those odds are even, meaning that there's the same chance of it being heads as tails, that is what we call a fair game. Now, there are unfair games, but that's another episode. So, a fair game, doesn't matter how many options there are, they're equally as likely. This has just as many chances as this. So what if we played, I don't know, 9 more times for a total of 10? What do you think would happen? If this is a fair game and the odds of me flipping for heads and flipping for tails are just as likely, well then, are the odds the same? Am I going to get the same amount of Oreos? Pause and think about it. If you got 5 Oreos on my plate and 5 Oreos for my kids, and I like the way you do math. So that's our theory. It's called theoretical probability. In theory, our math states that it should come up heads 5 times and tails 5 times. And that's awesome because now we've got this expectation of what should happen when I flip the coin. So what actually happens when I flip the coin? Because theories are great, but then there's real life. And when we deal with real life, we have what's called experimental probability. So now we're going to carry out a little experiment. 9 more times. one for the kids. One more for the kids. Starting to get hungry. Another one for the kids. And another one for the kids. And another one for the kids. I swear I'm not doing this on purpose. Another one for the kids. I just want another Oreo. Okay, thank goodness. Another one for my kids. What am I at here? It's 6, 7, 8. Two more. Come on. Yeah, there's one. And another one for the kids. So what happened? It was a fair game. I didn't cheat. I threw the coin in the air. It flipped. It landed. I should, in theory, have gotten half of the 10 Oreos. I should have 5. My kids should have 5. But that's not what happened. Because theoretical probability is based on great math and has great expectations. But experimental probability is what actually happens in real life. And as we know, life gets in the way. And this time, gravity decided that my kids are going to get 7 Oreos. And I only get 3. So what's even more amazing than all this is that there is a relationship between experimental and theoretical probability. And it's a pretty cool one. But I'm going to see if you can figure out what it is without me having to eat, well, a few cases of Oreos. So here's what you're going to do. We're going to simplify the game. Instead of piles of Oreos and trying to come up with coins for everyone, we're going to use a spinner. Everybody's going to get a spinner, a paper clip, and a pencil. Now, the spinner is half blue and half yellow, meaning that the odds of it landing on the blue are the same as landing on yellow, making this a fair game because the odds are equal. And in theory, if you, and you're about to, spin the spinner 24 times, you should get 12 blue and 12 yellow. But as we know, experimental and theoretical don't always line up. So what you're going to do, take your paperclip, put it on the center of the spinner, put your pencil on the dot in the middle, and flick. Yellow. Now my partner will write down yellow. And I'll do 12 spins and I'll let them do 12 spins. And we'll record blue. So far, so good. Experimental, theoretical, they're matching up. But what happens when I spin 24 times? And what happens when at the end we combine all of the numbers from the class and we add them up and find out how many blues and how many yellows we get? No greens, no mixing, no ties. What's going to happen? Well, that's for you to find out. But before you go on, make sure you can answer these 2 questions. Do you know the difference between experimental probability and theoretical probability? And do you know what it takes to make a fair game? Meanwhile, while you're doing that, I gotta play for the rest of these Oreos. Another one for the kids.